welcome to Silex, the podcast where we talk about scientific developments and technological changes in Luxembourg. Once again today, although remember, this is not always the case as we're also recently expanding to Europe. So we have European scientists, not only the ones based in Luxembourg, but today, as I said, we are again in Luxembourg, which means we are also proudly powered by Research Luxembourg and recording at the University of Luxembourg at the Media Center here. And our guest today is Professor Jan Lagerwall, who is a full professor of physics at the University of Luxembourg and head of the experimental soft matter physics group. Jan's research focuses on liquid crystals, colloids and polymers in unconventional contexts and forms such as shells, tubes and fibers. Jan, thank you so much for coming today.
Thank you for having me.
So today we'll be talking about many solutions to many problems. As I'm already hinting at the first discussion I wanted to start with, you are actually difficult in the beginning to prepare for an interview too, because you're doing a lot of different applications in different, I would say, fields. So your group has proposed many solutions to many different important life problems. Can you give us some examples?
First of all, I should say that all our research starts in fundamental science, fundamental physics mainly, sometimes fundamental chemistry. But we collaborate a lot with people who do completely different things, with different expertise. And when you do that and you have an open mindset and you are curious to learn about their problems, then you realize that there are many things where our research and our research results can be useful. So by collaborating with people from robotics engineers and computer scientists to artists and architects and medical doctors and so on, we find a lot of examples where our materials can be used in interesting ways. Some examples are, maybe the first one that we started working on seriously is anti-counterfeiting and supply chain traceability, and those are quite related. But recently we are working with structural engineers to monitor bridge health. So we've developed a material that can detect cracks in a bridge and then monitor if that crack is expanding. We're working with robotics engineers to both help robots navigate and to measure forces when they manipulate items in their environment. And hopefully we'll soon be starting a project together with a medical doctor who is specializing in robotic surgery and solving one of the key problems in robotic surgery. And that is that because the surgeon isn't anymore in contact with the suture thread, it's a robot that now holds the suture thread. A lot of times the thread breaks because the surgeon doesn't have a feeling anymore for how hard they are pulling at the thread. And of course, if that happens during surgery, that's a significant problem. So we're going to work on trying to solve that problem as well.
I love having scientists here who are experts in interdisciplinary research because it's just, I just love bridging those gaps that are just unnecessary, I believe, personally. But I also wonder, when you do that, how does it start? I guess, of course, it's a case-by-case situation, but you meet someone in a different field and they come with an issue or they tell you what they do and you say, wait a minute, we could apply our research to it.
It's very different from case to case. So the case with the surgeon was actually, he contacted me by email after we had published a paper on color-changing rubber fibers. And he then made me aware of this problem. In other cases, it's just friendship and a glass of wine and long discussions that can lead to many different ideas. And then, of course, here at the university, there are many opportunities for talking to people, learning about their issues, what they're working on, visiting their lab, inviting them to see our labs, to show our materials and so on. And then you let one thing come after the other, so to speak. There's no particular strategy or anything like that. I just like to have an open mindset. I mean, sometimes also another example, we are working with Phil Dale, who you interviewed here for a while ago, on making solar cells colored without ruining the efficiency. And that was also a little bit mediated by a master student working for Phil and then also involving me. And then Phil told me that colored photovoltaics is a huge thing, and I wasn't really aware of this. Then I realized that, well, maybe the way you color your solar cells now, which is very much related to what we are doing, could be done using our materials. And it turned out that that was actually very powerful. So now we have a joint project on that. So one step at a time, just keep on talking and listening.
Yeah, this is a good point, and also interesting that you mentioned the project with Phil, because I know it from a bit of a different side, because I also cooperate with the geographers. So I have been present in many different discussions about, people and their perception and what they think can be done with solar panels and what can't. And it's also very interesting from that perspective to have someone on board who is actually more about getting the buy-in, let's say, from the general public.
And it's also very motivating in a way when you see these opportunities, right? Also for my students and postdocs, I think, while they are fascinated by the physics we are doing, if they also see that they can hide a solar cell, so we might actually be able to roll out photovoltaics to a much greater extent, that's a very motivating insight for doing the research.
But we started with applications, and now I think we have to move on to what we know about your field. So, of course, a little bit of definitions and, just to understand what we are discussing here, could you make us a crash course? 5 minutes, hopefully.
Right.
So first of all, the materials. Let's start with the materials. Yeah. So what are you working with?
The group is called Experimental Soft Matter Physics. So soft matter is a very broad term for pretty much any materials that fall between liquid and solid. So in school, classically, we learned that there's solid, liquid, and gas, but there are actually a lot of states between solid and liquid. And maybe the one that everyone has encountered, it's our own body. So if you take your skin, your cheeks or something like that, would you say this is a solid or a liquid? Probably neither, right? And that's because it's kind of a rubbery material. And then if you go to artificial materials, well, rubber bands, rubber balloons, and so on, a rubber is a fascinating example of soft matter physics because it's a liquid that cannot flow. So if you think about why is a rubber band so incredibly elastic, it's because it's a liquid. But then you have to connect the molecules in it in order that you fix the shape. And then you have a rubber, which means that it's flexible because it's a liquid. But because of these connections, it stays where it is, so to speak. It doesn't change its shape. But this combination of liquid-like and solid-like is typical of soft matter. And then, of course, we work a lot with liquid crystals. And liquid crystals are liquid. They are not necessarily connected like a rubber, but they have long-range order that you otherwise only find in crystals. That's why we call them liquid crystals. Many people think crystals and solids is the same thing. That's not quite true. You have solid glasses. So your typical drinking glass, for instance, is a classic example. And it's a solid, but there is no long-range order in it. Whereas a crystal like diamond or metals and so on, they have long-range order. And that long-range order gives rise to quite specific properties, like specific optical properties, for instance, or response to magnetic fields or electric fields. And usually those types of properties that you see in crystals, you never see in the liquids. But in liquid crystals, you actually see them, although they're liquid. Application that most people know of that involves liquid crystals, that's liquid crystal displays or LCD. And the reason why the liquid crystal is important for the LCD is that because it's a liquid, it is easy to switch, to rearrange the order. But because it has this crystalline order, the switching comes with a change of optical properties. So effectively, when you switch between a dark and a bright pixel in your display, what you're doing is you're using an electric field to reorient the order.
That's a long food for thought.
Yeah,
I'm sure that when I'll
Sorry.
be editing, I will be re-listening to it a couple of times. So I do encourage you listeners, go back, listen again, because it's a lot to think of also because, of course, intuitively liquid is liquid. I can, pour it and not just have this structure as you were talking about. So yes, I will have to still analyze it later on. But you said liquid crystals and the application, the classic application, but it's pretty fresh. I mean, it's my lifetime when those screens appeared.
Yeah, but nowadays things go very fast, right? Especially in the science and research and so on, when we apply for grants, often people are expecting something in 5 years. In fact, I'm very fascinated about also how long it takes from a fundamental discovery to the application and breakthrough. If you think about many things that we're using today in our everyday lives, everything from Teflon pans to the laser in the supermarket cashier, microwave oven, it takes a long time often for them to go from discovery to application. And in many cases, that's maybe the most fascinating. There was no intention for any application when they were discovered. Do you know how the microwave oven was discovered?
No, I don't.
It was a research lab working in the field of radar. And the technician had a chocolate bar in his pocket. And he noticed that after an experiment, the chocolate bar had melted. And then they realized afterwards, when they were thinking through what is going on here, that it was actually the microwaves from the radar that was exciting the water in the chocolate bar and melting it. So a lot of interesting examples of how applications applications that are super important in the end, right? But it can take a long time. So back to your question about the time. Yeah, the first liquid crystal displays, they came in the late 60s. I would say the 70s was when it took off properly. And in the 80s, when I was a kid, that's when the first devices came for the masses, like watches, Nintendo. What were they called? Game Boy, I think, and so on. Yeah. And then the displays for computers, they came in the 90s, and then TVs a little bit later and so on. And now, of course, it's already a lot of alternative technologies, OLED, regular LEDs, and so on.
Exactly. That keeps changing. And that I kind of noticed once in a while when I'm in the supermarket. I'm like, oh, this is a new technology. Although I'm not a big fan of TVs in general, so probably I'm not the person to address this to. But that's one application. And I would say, okay, it's applied there and that's it. But no, I think there's a lot of research going on. There are societies for liquid crystals and papers and journals that I recently actually discovered, of course, as usual, when I'm preparing. So what is going on in the research, in liquid crystal research?
Yeah, I think since 10 or 15 years, the research community is really active in looking for completely new applications. So when I started my PhD back in the end of the 90s, display research was still kind of dominating the field. Conferences were still focused very much on displays, but it was already going down because the technology was pretty mature. Most of the really interesting display-related research was done in industry, actually. But I think since maybe 2010 or something like that, academic researchers are going in completely different directions. It's displays for us is now boring, to be honest. A lot of us are working on sensors, strain sensors, biosensors, chemosensors, and so on. Actuators, soft artificial muscles, for instance, that's what we work with a lot. Still, of course, a lot of optical elements that are quite fancy as well. Quite a few people are still using liquid crystal optics in a kind of way that is similar to what is going on in display applications, but it's not classical displays. And then, of course, you have the biologically related research. So one thing I didn't mention is that, our bodies are examples of soft matter, but we actually have quite a lot of examples of liquid crystals in our bodies as well, because every cell membrane is in a liquid crystal state. And recently, there have been quite a lot of discoveries that show how cells organize in the body. And there have been several papers where they find that certain types of organization, what is called topological defects, that are well known from liquid crystal physics since long, they are actually seen also in biological tissue, and people can now relate them to cell death and other biologically very important processes.
Okay, so there is a lot of papers you need to read. I can see also in biology in that case to just say, oh, look, this is basically what we know already in liquid. But what is the advantage of liquid crystals? Why do you want to use them for sensors, for example? We have sensors already. Why do you want liquid crystal sensors?
Yeah, what is quite magical about liquid crystals in particular, but soft matter in general, is that one of the definitions of Pierre-Gilles de Gennes, for instance, who I often consider the father of soft matter physics, is that soft matter is materials or matter with strong response function regardless of temperature, or at least over a broad range of temperatures. And what that means is that if you apply some kind of stimulus, it could be electric field, magnetic field, mechanical stress, or something like that, the system responds in a very strong way. And this is one of the key features that liquid crystals, for instance, change their optical properties, they can change their mechanical properties, their shape, even in response to quite subtle stimuli. For instance, if you take the case of biosensors, there are several groups that have shown that even very small concentrations of certain molecules can then induce a change in alignment that is then easily recognized by a switch from dark to bright, or colored to uncolored, or between green and blue, and so on. And The beauty of this is that you don't need any electricity. You don't need any external power at all, because this is just the liquid crystal itself that is responding. And a lot of sensors are electronically powered. So usually a lot of our technology is electronic, actually. So we also work a bit with the wearable tech and so on. And many people think about wearable electronics when they hear wearable technology. Our specialty is that we do non-electronic wearable tech, which has some advantages. First of all, there's no battery that's draining, right? It's always responsive. Second, you don't have to carry a battery, which is also interesting. If you remember when you're on a flight, they always tell you what to do if the battery catches fire and so on. And yeah, carrying a battery in your clothing maybe isn't always that attractive. So having responsive materials that don't need any electronics is actually quite interesting.
The responsive materials, when they respond, let's say, certain stimuli, is it visible for us? Or do we need also technology to actually notice it?
That depends on which type of material you're using and which type of response you're looking at. Indeed, there are some that really require polarized light to see the response, and that definitely is a bit limiting. But then you have materials like the ones I brought with me to our discussion here. They are very colorful, and they generate color by selectively reflecting a certain wavelength range. So it has a certain structure inside, and that, depending on the period of that structure, it reflects blue or green or red. You can then have stimuli that changes that period, and that means that the color changes. So you start with green and suddenly becomes red, or it starts uncolored and suddenly you see blue or violet or something like that.
So yes, you're showing, listeners cannot see, but I, of course, am going to share some links in the show notes where you can see the materials, because there are some already pictures on the web. You can check them out. And I also hope to take some pictures today so you can see as well. It's a fascinating thing. We also have some beetles here that Jan brought to show the kind of magic color that we're talking about here, the kind of green, violet, and in between bright. My daughter would be very happy here because she loves like glittery stuff, and that's kind of where I would put it. And also makes me think of 3D, watching films in 3D, because you brought the glasses too. So it's that kind of, if listeners, if you can use your imagination, I hope I described it well enough for you to understand what we mean. But I'm kind of in my head going back to the applications you mentioned in the beginning. So this activation of different colors, that's what you also want to apply in the anti-counterfeit project, or not?
It could be. At the moment, we don't do it. So far, I just talked about the strong response function. There is another very important reason why liquid crystals are interesting, and that is that they self-assemble or self-organize. So it's a very powerful feature that you have a liquid that you can process like a liquid. You can do any type of flow processing, microfluidic processing, whatever that you typically do with liquids. But then in that liquid state, the molecules organize in a very periodic or very regular structure. And that is incredibly powerful. So in the anti-counterfeiting application, we are using this type of a liquid crystal that is called cholesteric liquid crystal. It was discovered in a cholesterol derivative. That's why it's called like that. And they generate these very strong colors in a liquid state. A few years ago, there was, I would say, mainly a Dutch researcher called Dick Brouwer. He was working at Philips at the time. He realized that it would actually be interesting to turn those self-assembled liquid crystalline states into a solid. So he developed molecules that form liquid crystal phases, but they are reactive, chemically reactive. So you can polymerize these molecules into a solid. And his discovery has kind of given birth to a whole subfield of liquid crystal research. And that is that you use then the liquid crystal, first, the liquid crystal behavior as a kind of precursor to create a certain behavior, color in this case, and then you polymerize this, you turn it into a solid, and then you lose all that responsiveness, but that's okay, because what you're doing is you're locking in this self-assembled order into a solid that you can then use in a different way. So in the anti-counterfeiting application, we are making droplets or shells, so spherical beads or whatever you want to call them, that are made from these cholesteric liquid crystals. And because they start in the liquid state, that's why you can do this. You can make them bring them into this shape. And then by shining UV light, we trigger the transition from the liquid to the solid state, but they retain the optical properties. So you have each of these little beads is like a pixel. There's a picture element in the display, but of structural color. And structural color is this color by reflection. And by then combining different beads, you get a pattern of these reflection colors that also have a specific optical property called circular polarization. I don't have to go into it in detail, but it's something that the human eye cannot see, but it's very easy to detect it with simple technology. And what we do in the anti-counterfeiting application, and we have a company now that we launched called Trace Crystal, so you can look up tracecrystal.com and you can read more about it, is that we coat a surface that we want to protect with these beads. And every time we prepare a surface with maybe 100 or maybe 1,000 beads, they're very small, we have a certain randomness in this way, the distribution of the beads. And even we cannot control how they are deposited. So that means that every time you create the surface, you create a unique object. And it's very difficult to fake this because, as I said, even we cannot do it the second time exactly the same way. And because of this polarization and the type of color, you cannot just take a color printer and duplicate it, or even a 3D printer would not be able to do that. So it is really unclonable and unique. And that's why it's very powerful for anti-counterfeiting.
Sounds very interesting. And what also makes me interested even more is this whole idea of turning liquid crystals into solids, so containing them in some way, right? First of all, normally you have to keep them in a container, because I'm still thinking applying, it's a liquid state, right? So they have to be somehow contained somewhere or not.
Yeah, so when you start, often you have them in a bottle, and almost every liquid crystal in a bottle looks white. It looks like a cloud. And anything that looks white, whether it's milk or a cloud or just white paint, it's due to scattering. And a liquid crystal in a bulk sample like that is scattering light a lot. So in order to use the liquid crystal properties, or at least optical properties, let's say, whether it's for a display or it's for anti-counterfeiting and so on, you have to get it to a thin layer. So at least in one dimension, it has to go down to maybe 10, 20 microns. So that's, what is that in millimeter? It's a hundredth to 200ths of a millimeter or something like that. And then in the perpendicular plane, it can be large. That's not a problem. You can make a square meter size. That's fine. But in one dimension, you need to get it down to this thickness range, because otherwise thermal fluctuations, just temperature, right, variations will ruin that order, the uniformity of the order, and then you get to the scattering state again.
And that's how also our LCD screens are protected, I guess. Somehow they have to have some layers like that too.
Yeah, so in that case, you have two glass slides or glass planes, or whatever we should call them, and the liquid crystal is in between them. So when I started as a PhD student, we often filled liquid crystal displays or cells from one side. So you first made the glass slides, and then the liquid crystal went in by capillary force on one side. And of course, that's not possible with today's displays, because it would take ages to fill a single display. So nowadays, it's an amazing process. There is so much engineering behind display fabrication. And it's really, you have these robots that handle these enormous glass window panes, right? But super flat. And then you spray the liquid crystal in between and you put the second one on top. And it's amazing to think about it. But you know what the gap is between the glass slide and the display? It's on the order of 3 microns. And it has to be exactly 3. If it goes down to 2.5 or 3.5, the properties are ruined. I mean, you know how large a TV is today, right? And imagine that over that area, everywhere, the gap is 3 microns.
Okay, it's really a feat of engineering that we're talking about right now. But you mentioned that researchers right now are not very interested in these, so we can leave them there.
But I'm always fascinated about engineering solutions. That's also funny that a lot of my colleagues, they kind of, and that's engineering. We're doing physics. And of course, I love physics. But whenever I see engineers in action and I see a factory, it's amazing how they can make that and so on. I find it fascinating.
Totally. And, on the subject of the applications you mentioned, what I always find fascinating is when engineers are building bridges and they start from two different sides and then the bridge kind of meets, obviously, because it has to. It's fascinating, totally. But before we move on to bridges and all the other applications we have, I just wanted to ask you one more thing about this containing liquid crystals, because I know that you look, for example, at putting them in shells. Why would you do that?
In one dimension, you want to make them a bit thin. The typical way you do that is then you have two flat glass slides and you put the liquid crystal in between. But if that's flat, that limits the behavior in many ways. That means that if you look at it at a different angle, you see different properties and you have edges and so on. When we bring these liquid crystals into shells, that gives some interesting properties. First of all, we still manage to contain them in 10 to 20 microns because that's the thickness of the shell. But now it's a sphere. And the first thing is that a sphere has no edges. So that's already quite fascinating that you get, from a topological point of view, it's a completely different object from a flat surface. And the best way to illustrate why that is important is think about the Earth. So the Earth has two topological defects. We know them usually by the names North Pole and South Pole. And if you're standing at the North Pole or at the South Pole, and someone asks you, where is North? You can't answer because the whole directional field breaks down in the topological defect. And a sphere has to have a certain amount of topological defects. You can't get around it. So that's for the actual Earth. But when you make a plane map of the Earth, you know that everything gets completely distorted at the top and at the bottom. Greenland, that everyone is talking about today, is very, very large, much larger than it is, and the North Pole itself, of course, right? And that's because you're expanding this thin point onto a much larger area. So the transition from flat to sphere is very, very deep. There are a lot of things happening there. And so you really get phenomena, and especially related to the topological defects, in the shell that you don't have in the flat sample. So that's more from a fundamental point of view, that this gives rise to a lot of interesting physics. Then from a practical point of view, is you saw on the samples that the color changes with viewing angle. And you can probably link to some videos or something like that after where the viewers can see this as well. But if you have a sphere, then because a sphere looks the same no matter from which direction you look at it, it's not completely gone, the viewing angle dependence, but it's very much reduced. And that's quite useful because the viewing angle dependence is interesting, but it can be a complete nuisance for many applications as well.
All right. So that this, again, opens another Pandora box, if I may call it like that. Just, I keep looking at the watch thinking like, oh my God, we haven't really discussed almost anything. And it's only 30 minutes. It's just so fascinating. I have to say that I feel even a bit bad because nowadays I spend so much time reading about quantum physics, and I have a feeling I should read more about soft matter physics because it's a completely new world unknown to me, and there's so much going on. And we just talked about liquid crystals, and there are so many other things we need to discuss, and one of the things are the rubbers, right? So before you tell us more about the rubbers, you prepared also a pub quiz question about them. So if you can ask the question right now, and listeners, remember, answer only at the end of the podcast.
Okay, so consider a rubber band and imagine that you make an ideal rubber band. What do you think is the minimum number of molecules? Make a rough estimate that you would need to make an ideal rubber band.
And remember, answer only at the end. And I can't wait to solve it because the answer is very, very surprising to me, at least. I'm not hinting on anything, but keep thinking and we will reveal it at the end. Okay, so rubbers, I said. Officially liquid crystal elastomers, if you're using liquid crystals, of course, for rubbers, right? So what are they? What are their characteristics?
Yeah, so elastomer is kind of the scientific word for rubber. It's the same thing. A rubber, as I think I mentioned before, it's a liquid that can't flow. And a liquid crystal rubber or liquid crystal elastomer is a liquid crystal that can't flow. It's a little bit like with a regular rubber. A regular rubber is a polymeric liquid. Polymers are very large molecules. And just because they're very large, they get some quite fascinating properties. And if you then connect maybe 5 or 10% of these molecules, or you have a connectivity of about 5 to 10%, then you get a rubber, which means that you can stretch it, you can deform it, but it cannot flow anymore. And with liquid crystal elastomers, it's very much the same principle, but we start with an ordered liquid. We start with the liquid crystal, and we connect 5 to 10% of this material, and we get then the liquid crystal rubber.
Still thinking of the liquid definition. So I always thought that liquids have to flow, and you said it's a liquid that can't flow.
Yeah, but that's a fascinating thing about rubbers. It defies many classical definitions, right? So a rubber is a solid from a macroscopic mechanic property point of view. So indeed, it doesn't flow, which is from a classical mechanics point of view definition that it's a solid. It keeps its shape. You put it in a bottle, it will not take the shape of the bottle, it keeps its shape. So from a macroscopic point of view, it's a solid. But at the molecular scale, the molecular dynamics are those of a liquid. So the molecules, they fluctuate like crazy, and if you wouldn't have those 5 to 10% crosslink, it would flow. So in that sense, it's at a molecular dynamics scale that it is a liquid. And that is important because if it weren't for that liquid state at the molecular scale, you wouldn't have the elasticity.
Okay, we have the materials, loads of them. Material engineers have come up with so many different types of rubbers. Even in my questions to you, when I send them, I call them ordinary rubbers. I don't know if you can say that, ordinary rubbers. Why introduce liquid crystals then?
Yeah, so the fascinating thing with liquid crystal rubber is that now you combine those special properties that liquid crystals have with the elasticity of rubbers. So, for example, if you take cholesteric liquid crystal, these ones that have the structural color, they then show this color, but now the period which defines the color, it couples to the shape of the material because of you have turned it into rubber. So you can stretch this like a regular rubber, but as you stretch it, if you imagine you have a film and you make it longer in one direction, because it's a liquid, it has to deform at constant volume. And that means that if you make it longer in one direction, it has to get thinner in the perpendicular direction. And if that direction is the direction of this periodic structure, which is what we try to achieve, then that means that the color changes. So if you start with a red rubber, for instance, as you stretch it, it gets orange, yellow, green, blue, violet. And that will not happen unless you have this connection of liquid crystalline order with rubber behavior.
Is the color related to the behavior, or can you choose really which color you start from and which one you end up with?
It is related to the behavior in the same way as the colors of the rainbow are always in the same direction. So the color comes from the period. When we deal with colors in this sense, maybe you have heard that light can have a particle or a wave nature. Here, usually the wave nature is the easiest model to work with. So then you say that, okay, a colored light has a certain wavelength, and the longest wavelengths that we can see, they are red. And if you start with this red rubber, that means that it has a long period, long in the sense that the period is the same as the wavelength of red light. And what happens in this case is called a Bragg reflection. For those who studied X-ray crystallography, they will recognize this term. That light cannot go through, so it's reflected. And when you stretch the rubber, the period is reduced, and then the wavelength that cannot go through and is reflected is shifted, so to shorter wavelengths. And that's why you cannot really change this. It always goes from a red towards violet as you stretch it, because you're going from long to short wavelengths.
Listeners couldn't see it, but while you were talking, exactly, we have some lights changing here. And when you started saying red, it actually changed into red. It was a magical moment. I don't know what's going on, but yes, that was the right wavelength. So maybe exactly good context. All right. This also reminds me, I heard about a very good test when you are a deep diver and going down. You actually can take the billiards balls with you. Different colors. Mm-hmm. And with the colors, you can actually see how deep you're going, because you will stop seeing certain colors at certain, depths. Cool. Okay. Very interesting thing. Yeah. Of course, I don't know, why would you carry them? Because they're a bit heavy, but maybe that's in the past, especially without the right, tools, maybe that could be a solution.
Probably bring a color chart would probably be the same thing, but it's an interesting point.
Yes, exactly. So just, a side note, let's say. I think it's the moment to mention at least one project name of yours, because, normally when I have the guests here, we sometimes just use all the abbreviations like there is no tomorrow. And so far we've avoided that. But there is a name that I really particularly like, which is Alchemist, right? So we're talking about rubbers and applications. So what is Alchemist about?
So Alchemist is our newest project, starts on 1st of March, and it's a collaborative project. It's called ERC Synergy Grant. So it's me here in Luxembourg, and then there is Professor Maria Elena Godinho in Lisbon and Professor Eugene Terentьев at Cambridge University. That project will explore a completely new chemistry for making liquid crystal elastomers. So the idea is to make them sustainable. The stuff I brought with me today, they're all oil-based, petroleum-based, basically. And that's almost everyone working today with liquid crystal elastomer uses these materials that are petroleum-derived. And in Alchemist, we will work with cellulose and chitin instead. And these are naturally occurring polymers. Cellulose is the most abundant polymer on Earth, actually. And other so-called polysaccharides. So on the one hand, we're kind of moving towards making them more green in this respect. On the other hand, it's also a little bit a different way of making the elastomers, because these elastomers that I show you today, they're all made from small molecules, and then we let the liquid crystal form, and then we polymerize and cross-link and so on. Whereas cellulose and chitin, they are polymeric from the beginning. And a lot of cellulose derivatives, they actually form liquid crystal phases. And by the way, the beetles, that's chitin. You find cellulose in plants, and you find chitin in insects, crustaceans, and so on. So these are examples showing that they form liquid crystal phases. We're going to process these materials in a quite new way to get liquid crystal elastomers the way we want them. So on the one hand, it's all about turning the chemistry green. On the other hand, it's about processing the material in a really new way in order that we can also make much, much larger samples. Because I didn't say so much about liquid crystal actuators yet. So these ones that change color, they are as sensors. But you can also have liquid crystal elastomers that change their shape. So really working like artificial muscles. Quite a few people are working on this today, but they usually make like tiny samples, 1 square centimeter or something like that. And it's in the lab, and you publish a paper and you're happy. But of course, if you want to use them, you really have to make significant amounts. They have to be large and so on. And most of the processing methods today, they are not really compatible with that. It will be way too costly. It's difficult to make it really in the size that you want. So the project is very much about also developing completely new processing methods that allow us to work with square meters instead of square centimeters.
And on top of it, again, materials that look very nice, right? Because we can assume that if the moment you're actually applying liquid crystals and elastomers in this case as well, you can count on nice colors, right? Or not necessarily?
Well, it depends on what you mean with nice.
I am actually alluding to an episode that I had a couple of months ago with Tim Huber from List, where we were talking, can sustainable materials be beautiful? Mm-hmm. And exactly this whole idea, he's on a quest to actually convince material engineers that it's all about the properties, but also the way the materials look. That's why I'm asking you about that. Nice in the sense, as we sometimes tend to think sustainable material is in the shade of brown.
No, that's true. No, I get your point. Yeah, absolutely. You can make these definitely very colorful. You can definitely make what is called spectral colors, like these strong green and blue and so on. And then if you want to make non-spectral colors, which are mixed colors, that can be a little bit more tricky. But that's why where these shells also come in. Because as I said, they are pixels of structural color. And by mixing them in different ways, we can also generate non-spectral colors. So yeah, I would say we will definitely be able to make them look beautiful.
Okay, so then definitely go talk to Tim about that as well, still based in Luxembourg, finding you another, partner for a glass of wine and discussions.
Yeah, he's also working with cellulose. So
yes, exactly. Okay, I think we have the rubbers, we have the liquid crystals in general. And we did hint in the beginning on the bridges project, so I think we can move to that and maybe we'll have a little bit more time, but I'm not so sure because, as I said, it's going very fast. So what about the bridges? Like you put some of your materials in and then it changes color to say, oh, there's a crack. Is that more or less it? Or I didn't get it.
Yeah, we don't put them in, we put them on.
Okay, sorry.
So that was a project that started in a discussion with Danielle Waldmann-Diederich. She was at the Department of Engineering at University of Luxembourg before. Now she's in Darmstadt. And she taught me that a concrete surface comes pre-cracked. It's full of cracks. So even when it's completely new, there are lots of cracks. That's not a problem. The problem is when a crack grows. And that's interesting because we had these liquid crystal elastomers or rubbers that were changing color, and we were really discussing with a lot of people, what could we do with these? And of course, a lot of people would say it's completely ridiculous to compare concrete that has no elasticity, especially in stretching, and rubbers that are very soft. But the point was that when she mentioned this, that the critical thing is when you have a very small crack that is so small you cannot see it, and then it starts expanding, that means that very locally you have a very large strain. So the concrete on it overall is, of course, not strained at all, but where the crack happens, you have a strain of 100% or something like that, or infinite, in fact, very locally. And that means that you can cover the concrete with our rubber, and because that infinite strain is now distributed over the thickness of the rubber, you get a strain of maybe 50 or 100%. And what then happens, and that's what we demonstrated in our collaboration with her, is that if you start with the red covering, for instance, then suddenly it becomes green where the crack appears. And as the crack grows, that green turns into blue and turns into violet and so on. So we have now developed a method that we can spray coat these rubbers. Initially, we thought we would make them first and then glue them onto the concrete. But we realized it's much easier if we can spray coat or brush coat. Both are possible. And now Danielle is no longer in Luxembourg. We're still working with her, but we have a local collaboration with Numa Bertola, who is now a new professor at engineering. And there we just, with the Institute of Advanced Studies, we got a new project where we will spray coat a bridge that he is already working with in Switzerland. He's from Switzerland originally. And the idea is then to see if we can monitor cracks as they develop in a real bridge in outdoors, because we have already demonstrated that it works in a lab. But now the interesting thing is to see, will this also work out when we leave the bridge to the forces of nature for a couple of months and years.
How thick would the layer have to be that you spray coat?
About 10 to 20 microns. Or even, I would say 5 is probably the minimum. It's also part of the research to estimate this. If you just think about the optical properties, you would need at least 5 microns. But then there is this thing about distributing the infinite strain over the thickness. And that's something we have a qualitative understanding of, but we haven't quantified it. So that's going to be part of the research.
And then would it be visible to a normal human being that the crack is, propagating, or just to the engineers who have a special type of, tool to monitor the whole bridge?
So our idea is definitely that anyone should be able to see it. I generally am very much in favor of when there is a problem, anyone should be able to discover and report it. But of course, other people may disagree. And the question is a little bit how it would look, right? So at the moment, we are targeting inside areas of the bridge that people don't usually see. So unless they go underneath the bridge and look up, they wouldn't actually see it. But in the end, you could imagine painting an entire bridge in this material. And the question is then, is it a feature or a bug that the bridge will change color as the sun sets, for instance? That's an interesting aspect.
That is exactly, because I was thinking that it's just doing two things at the same time, right? Adding certain property, look and feel that is not necessarily only for monitoring cracks, but something else. So yeah, why not? I don't know. Depends on the Swiss as well, because I guess they'll be deciding what they want really their bridge to look like. You're so good at science communication that you're not using some of the buzzwords, and then I'm not sure whether we have explained this or there is something that is missing. And when you read your articles and you go deeper into your research, you have, of course, liquid crystals, you have the elastomers, and then you also have the cholesteric spherical reflectors. So the reflectors are something else than the liquid crystals in the sphere, as we were saying, in the shell, or not?
No, they are the shells or beads. The cholesteric spherical reflectors, we use that as a collective term for all spherically shaped cholesteric liquid crystals. And we use them as we make beads, so kind of solid droplets that we turn into a solid, or we use them, make them as shells. And the two have a little bit different optical properties, but this spherical reflection is common to them.
Okay, so then I am clear right now. So as we said, for the counterfeiting, that would be an application, right? In case of other applications, I noticed something about disease control. What's the application there?
Yeah, so that's a project that we're working on together with Shiva Krishnamurti at LIST and Carol Linstar at LCSB. There are two aspects of it. One is it has nothing to do with the cholesteric beads. It was inspired by the pandemic, so it was a pandemic-born project, let's say. And the other aspect is simply about the really unpleasant way of sampling, with sticking a swab into the nose or into the throat. And so part of the project is just about using face masks. So you simply breathe into a face mask, and then you remove a part that you have breathed on, and that's your sample. But the part with the spheres is that because it's so easy to make them in different colors and to give them these different polarizations, right-handed or left-handed, we can actually very easily distinguish one type of sphere from another, and we can easily detect them also with very high contrast. Because if you take two images of the same scene, once through a left-handed and once through a right-handed polarizer, then everything that is not cholesteric looks the same. So if you now subtract one image from the other, you just get black for anything normal, let's say. But the cholesteric, they are colored in one image but not in the other, so they remain. And that means that you can then have very, very strong contrast if you would be able to use these types of beads as indicators of a disease. And the reference now is the standard rapid antigen test that we all use during the pandemic, or if you try to get a baby, you have used it with pregnancy tests and so on. You probably know that it's pink on white. And pink on white is pretty bad contrast. And in order to see for sure that you have COVID or influenza or whatever it is it's testing for, you actually need millions of virus particles in that sample in order to actually get that color. And in this project, we've been working on coating our cholesteric spherical reflectors with biologically active molecules, with the antibodies for the proteins that are relevant to the detection. So spike protein, probably everyone remembers from the pandemic time for COVID. And instead of these beads that you have in a commercial rapid antigen test, which is a plasmonic gold nanobead or a latex bead, you would have these spherical reflectors. And the beauty of that is that because of this contrast enhancement that is possible because of the polarization, you would be able to detect that you have the disease at much, much lower sample concentrations. And the other beauty is because you can make, for instance, red beads detecting COVID and green beads detecting flu and right-hand, left-handed beads and so on for other things. You could have one test for multiple diseases. So you just use one test, you put one sample in it, and depending on which disease you have, you see then a different color or a different polarization, and you would be able to detect that.
Sounds like an ideal solution. Why isn't it used yet?
Well, we're working on getting the beads coated with the right biomolecules, but we have pretty good results. My postdoc, Yong Geng, he is in the process of preparing the first paper demonstrating that it is possible to use these beads for the purpose.
Okay, so fingers crossed for sure. Did we discuss most of the projects you're working on, or we skipped something? Because there's so much, and I didn't want the listeners to just be a bit lost, so to be able to navigate all this, right?
We can save it for next time.
We can save it for next time, exactly. You might be one of the first guests that I re-invite, because so far there hasn't been a second time, but who knows, because there's really... I'm pretty sure that there'll be more discussions going on with more people and new applications that come out of it. And also you can tell us of all the successes, hopefully, fingers crossed, of all the things that are going on right now. And before we say goodbye, of course, we have to solve the pub quiz question. So we're going back to the rubbers, right? And the question you asked, as usual, if you can repeat the question once again, because maybe people don't remember it anymore, and then let's solve it.
Right. So the question was, if you have an ideal rubber, really ideal, what would be the minimum number of molecules that you would need to make this, or rubber band? I think I took a rubber band, but you can apply the same thing to a rubber balloon or an eraser or whatever rubber object that you typically come across. So how many molecules would you need? And the answer is 1. Because the defining feature of a rubber is that it's a continuous network. It's a liquid that cannot flow. And why is it a liquid that cannot flow? It's because all the molecules are connected into one network. Now, in practice, there are more than one molecules because in most commercial systems, you don't have a perfect connectivity between every molecule. But it's very, very low number compared to if you think about how large the object is. So in principle, you could basically complain to your supermarket that you're charging way too much for your balloons, like a few euro for 10 molecules. That's not okay.
I don't think they will really listen to you.
Probably not.
But listeners, if you feel like trying, let us know if it worked out. I mean, it would be very interesting to know that someone listened to such a complaint. But yeah, in general, with balloons, I think the biggest suffering for me is the fact that some of them are just extremely difficult to blow. So especially, the pressure of kids coming, Mom, I want my balloon. And then you're just trying and it just doesn't go. So yes.
Until you get it going, then it goes easier.
Yes, exactly.
But threshold.
Yes, totally. But there's also the quality of the rubber that really influences that too. So yes, that these are my struggles normally. But whatever, this is just behind the scenes discussion. Thank you so much, Jan, for today, for sharing all this. Listeners, remember also a lot of show notes are going to be shared with you, so you can check out what we were discussing. Thank you.
Thank you so much for having me. It was a pleasure.
And this is it for today. Don't forget to subscribe, to follow us, to check what we are writing on all the social media where we're present. So yes, we are there on Blue Sky, Instagram, LinkedIn. Suggest guests, support us as well. Remember, we are on Patreon in case you want to chip in for our growth. This was Silex, and my name is Hanna Siemaszko.